Let's work on some investigation to connect the graphs of derivatives together. So first off, we're going to start by graphing f of x equals x cubed. We know that the base graph points are -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. And we can connect the points using a smooth curve to the best of our abilities. Now, where does there appear to be a point of inflection on the graph of f of x? And point of inflection is really where the graph changes from concave up to concave down, or concave down to concave up. So essentially where the direction of concavity changes. And it looks like from our graph that to the left of x equals 0, the tangent lines would lie above the curve, and to the right, the tangent lines would lie below the curve. So I'm going to say that right now, it appears to be at x equals 0, so at the point 0, 0. So now we know that the first derivative is going to be f prime equals 3x squared, and the second derivative will be f double prime equals 6x. So we're going to graph both of those now on the same grid. Just let me label this. This is f of x. This was f prime. So there are my three functions, f of x, f prime, and f double prime. Now show algebraically that the point where the first derivative, f prime of the function, is equal to 0 is 0, 0. So we want to figure out where f prime equals 0. So that's 0 equals 3x squared. So obviously this is going to be x equals 0. Now, for the interval where x is less than 0, the first derivative of the function is above the x-axis and is therefore positive. And then an increasing function because the first derivative is positive. Now, for the interval where x is greater than 0, the first derivative is also above the x-axis and is therefore positive. So on this interval where x is greater than 0, the function is increasing. Now we're going to show algebraically that the point where the second derivative of the function is equal to 0 is also at the point 0, 0, which we can clearly see on the graph. But to prove this algebraically, we're going to set our f double prime equal to 0. So that's 0 equals 6x. So obviously, x is equal to 0. Now, for the interval where x is less than 0, the second derivative of the function is below the x-axis and is therefore negative. And when the graph of the second derivative, and when the second derivative function itself is negative, that means that the original function is concave down. Let me move up the page. And then for the interval where x is greater than 0, the second derivative is above the x-axis and is therefore positive. So when that second derivative is positive, that means that the original function, f of x equals x cubed, is concave up. Excuse excuse me. Describe the behavior of the second derivative of the function to the left and to the right of the point where the second derivative is equal to 0. So this means that the second derivative is negative to the left of x equals 0. So f of x is concave down. Then f double prime is positive to the right of x equals 0. So f of x is concave up. So this implies that when the sign of the second derivative changes from positive to negative or negative to positive, and f prime prime at some point c is equal to 0, then x equals c is a point of inflection. And to specify, I'm saying that this changes positive to negative or negative to positive at x equals c. Okay. Let's move on to the second part of the investigation to see how transformations will affect concavity. So go on to page 2. So this time we are going to graph g of x equals x cubed plus 2, which is the graph of f of x equals x cubed translated 2 units up. So we're going to graph both of these functions on the grid. 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. So this is my original, my original function f of x equals x cubed. Let me just fix my little mistake there. And I'm going to also graph my translated function g of x equals x cubed plus 2. So all of these points, 2 units up, 2 units up, 2 units up, and 2 units up, and where was I? 8, 7, 6, 2 units up. So this is my graph of g of x. My original was f of x. Okay. Now we're going to graph the first derivative of g of x, which is still g prime equals 3x squared, because this constant term of 2, its derivative is 0. So we're still going to graph basically the same functions as on page 1. There's my first derivative in purple. And then my second derivative is again going to be g double prime equals 6x. This line with a slope of 6 and passes through the origin. So, answering number 2, where does there appear to be a point of inflection on the graph of g of x? So looking at the graph of g of x, I think that our point of inflection is right here. So it looks like the point of inflection is at 0, 2 on g of x. And we can compare that to the point of inflection that we found for f of x, the original function, which was at 0, 0. Okay, so now skip step 3, we already did that, sorry. Now show algebraically that the point where the first derivative of the function is equal to 0 is at 0, 2. So again, if we want to set the first derivative equal to 0, g prime equals 0, so 0 is equal to 3x squared, so that means x must be 0. And then when we figure out what g of 0 equals, then that's 0 cubed plus 2, which is 2. Okay, so therefore g prime x equals 0 at the point 0, 2. So now for the interval where x is less than 0, the first derivative is above the x-axis and is therefore positive. And when the first derivative is positive, we know that the function is increasing. When x is greater than 0, the first derivative is above the x-axis still, and therefore also positive. So that means on the interval x is greater than 0, the function g of x is increasing. Oh, sorry, let me move that up. So now we're going to show algebraically that the point where the second derivative is equal to 0 is also 0, 2. So that means g double prime equals 0, 0 is equal to 6x, so we know that x is equal to 0, and again g of 0 would be 0 cubed plus 2, which is 2. So g prime, double prime rather, is equal to 0 at the point 0, 2. And again, for the interval where x is less than 0, the second derivative is below the x-axis and is therefore negative. So for this interval, the function is concave down. For the interval where x is greater than 0, the second derivative is above the x-axis and is therefore positive. So for this interval, the function is concave up. So describe the behavior of the second derivative function of the function to the left and to the right of the point where the second derivative is equal to 0. What effect does translating a function vertically upwards have on the location of a point of inflection for a given function? So it turns out that our answers here and here were identical, here and here as well, as the part A investigation. So a vertical translation upwards has no effect on the x value of the function where we have a point of inflection. The only thing that the vertical translation affects is where the y-coordinate will lie, because obviously now that we've thrown in a vertical translation, that will change the y-coordinate of the original function. Okay. So it turns out that in fact a vertical translation will not change anything else about the function in terms of, whether it increases or decreases on an interval, okay? As well as where local extrema are located. So let's move on to the last investigation, part C. So in this part C investigation, we're going to do a little bit of working backwards in one sense. So we have, the instructions are sketch and label the graph of the function g, which is a straight line with slope 2 and x-intercept at the point 2, 0. So x-intercept at 2, 0. Slope of 2 means I go 1 to the right, 2 up, 1 to the right, 2 up, 1 left, 2 down, 1 left, 2 down, etc. So this is my graph of g of x. Suppose that g of x is the derivative of f of x, and f of 0 is equal to 6. Sketch the graph of y equals f of x on the same grid. So now I have to plot my point 0, 6, okay, because this is what I was told about f of 0, it's at 6. But aside from that, I have to do a little bit of reasoning to determine that, well, if this is my first derivative of f of x, and I have an x-intercept or a 0 at 2, 0, that means that I should have a local maximum or minimum at this point on the original graph. And because my first derivative is negative to the left of x equals 2 and positive to the right of x equals 2, that means that the function was decreasing up to 2 and then increasing afterwards. So one possible sketch would be if I were to follow like a regular step pattern for the quadratic. So 3, right here, 1, 1, 1, 1, 1, 1, 2, 3. So this would be one possible sketch of the original function f of x. It meets all the criteria that I know about f of x from its first derivative function. The fact that it's decreasing until x equals 2, the first derivative was negative. It has a local minimum at x equals 2, that's why the first derivative was 0. And then after that point, f of x was increasing. That's why g of x is positive when x is greater than 2. So now for the last part here, suppose g is defined by the equation g of x equals 2x minus 2. Determine the equation of the second derivative and describe some key features of the graph of the original function. So let me see here. To figure out my second derivative, well, I'm given the equation that g of x is equal to 2 times x minus 2, which is really 2x minus 4. So in order to find the derivative of g of x, which is really the second derivative of f of x, that's going to be 2, right? Derivative of 2x minus 4 is simply 2. Okay. So based on this, we need to give a few key features about the original function. Before I do that, let me just sketch what, or graph what the second derivative looks like. This is a horizontal line going across y equals 2. So I have my I have my original function here. I have my first derivative, g of x, which is really f prime here. And then I have my second derivative, f double prime, which is the horizontal line going across y equals 2. So, some key features of the original function, f of x. We can see that it's a quadratic, since the degree of g of x is 1, right? If we have a linear function for g of x, we know that f of x has to be quadratic because the derivative is always 1 degree less than the original function. So that means that the original function has to be 1 degree higher than the derivative. We also know that the function is always concave up. And aside from having the sketch of the graph to show us this, we also know this because the derivative of g of x was positive 2, which is always positive. So since the second derivative was always positive for xer, that means that the function must always be concave up. And the other thing that we figured out early on was because the sign of the first derivative changes from negative to positive at x equals 2, that must be where the local minimum rests. And last but not least, because the first derivative equation is 2x minus 4, if you try to work with this backwards into what the original function equation should be, this 2x is a result of bringing down the exponent and then changing the exponent from 2 to 1. So that means this coefficient should have originally been just 1 because you brought down the exponent of 2. So the algebraic model should look something along the lines of x squared, and then this negative 4 has no x term next to it, so that means that in the original function it did have a negative 4x, right? And then the last term we don't have really, it's a plus 0, which means that in the original function, that means that we had to have k, some value k where k belongs to the set of real numbers. In this example specifically, k should be equal to 6 just because we specified that f of 0 should equal 6. But if this was not specified, then really this parabola could be translated up or down anywhere, and we would still get this same g of x and this same f double prime. Okay, let's move on to the last example. So again, sketch and label the graph of the function g, which is a straight line with the slope of negative 2 this time and an x-intercept at 2, 0. So there's my function of g of x. Suppose that g is a derivative of f and f of 0 is equal to negative 6. Now we need to sketch the graph of y equals f of x on the same grid. So f of 0 is at negative 6. And again, using the same line of reasoning as in the previous example, we see that the function is positive up until x is equal to 2, so that means that the derivative is positive up until x is equal to 2, so that means that the original function must be increasing up to x equals 2. Then at x equals 2, we have a derivative value of 0, so that means the original function should have a local maximum. And then afterwards, the derivative is negative, so that means that the original function should now be decreasing back down. So here's my sketch of f of x, keeping in mind that g of x is actually the first derivative of f of x. So again, let's do this work. It says g of x is equal to negative 2x minus 2, and we need to figure out its derivative, which is really the second derivative of f of x. So that means we will have, let me pick a different color. Purple. The second derivative of f of x, which is really the derivative of g of x, is going to be negative 2. So I have a horizontal line going across y equals negative 2. And again, based on this, we can state some key features of f of x. Again, we know that it's quadratic since the degree of g of x is 1. Unlike example 1, in this example, the function is always concave down. And we know this because our second derivative is always negative. So when the second derivative is always negative, the function, it turns out, is concave down. And then we already discussed this earlier when we were sketching the graph. We have a local maximum at x equals 2. Sorry, so I should change that up here. It's not local minimum at 2, 0. It's local minimum at x equals 2. My apologies. There we go. So going back to this example here, local maximum at x equals 2, because the sign of the derivative changes from positive to negative at x equals 2. And last but not least, again working backwards from the algebraic model of g of x, we can conclude that the algebraic model of f of x should be something along the lines of negative x squared, and then that's how when you take the derivative you get negative 2x over here. Okay, and then, sorry, oh, so many mistakes on this one. This is actually plus 4. So the algebraic model is f of x equals negative x squared, and then the original function that gave us the derivative of 4 should be actually plus 4x, and then the constant value k turned into 0 when we took the derivative. Okay. So that's it for this lesson. Sorry about all the mistakes.